From this presentation onwards, we are starting with this new chapter called partial orderings, and in this particular presentation, we will discuss all these topics one by one. Why do we study partial orderings? This is a very important question for us to understand. What is the need of studying partial orderings? Then obviously we will discuss the definition of partial ordering, and then we will understand what is a poset. And it is equally important for us to discuss some examples on partial orderings. After that, we will discuss the difference between comparable and incomparable elements. So without any further delay, let's get started. Many a time we use relations to order some or all the elements of a set. It is important for us to understand that ordering is very important, right? We used to order elements in real world as well. Let me tell you that we use relations, okay, to order some or all the elements of a set. How? Let's see this with the help of an example. Let's say we have a set of all words in the dictionary, okay? And let's say we have relation R, which consists of all ordered pairs of this form A, B, such that A comes before B. Understand this, we are considering two arbitrary words from this dictionary, and here we are putting this condition that A must come before B. If you closely observe this relation, then you can find that this relation is helping us in forming the order. That is, this relation is ordering all words in the dictionary. Isn't that so? Here you can see the example. We know that partition, this word partition, comes before this word relation. Why is that so? We can see the first letter of these two words, right? And compare them. You can see that here we have P and here we have R, right? We know that P comes before R, therefore partition comes before relation. So we can form an ordered pair of this form, that is partition, comma, relation, right? Here obviously partition comes before relation, that is why partition is placed before relation in this ordered pair, right? It is not the case that relation comes before partition, therefore we do not have an ordered pair relation, comma, partition, right? So this relation is helping us in ordering all the words in the dictionary, right? Let's see one more example. Let's say we have a set of all integers. Let's say we are available with a set of all possible integers. And we have a relation R which consists of all ordered pairs A, B such that A is less than B. If you closely observe this relation, then you can find that this relation is also helping us in ordering all integers. That is, forming the sequence of integers where the first integer is less than the second and second integer is less than the third, and so on, right? In the previous examples, we have seen how a relation indicates that a certain element precedes the other in the ordering, right? These relations are used to order some or all elements of a particular set. We know that R1 is helping in ordering all words in a dictionary, and R2 is helping in ordering all integers, right? Here obviously ordering depends on these conditions that we have specified, right? Now let's say we also add pairs of the form A, A in R1 and R2. Currently, there are no such pairs possible in these two relations. But let's say we add all the pairs of the form A, A in R1 and R2. And the relation so obtained will look like this. R1 must consist of all ordered pairs A, B such that A comes before B or A is equal to B. And R2 must consist of all ordered pairs A, B such that A is less than or equal to B. We have obtained relations R1 and R2 that are reflexive, antisymmetric, and transitive. If you closely observe these relations, then you can find that these relations are reflexive, antisymmetric, and transitive. Why is that so? Obviously, these relations are reflexive because we have added the pairs of the form A, A. Apart from this, these two relations are antisymmetric as well because ordering is there, right? When we say A comes before B, then it is not the case that B comes before A, right? When we say that partition comes before relation, then we cannot say that relation comes before partition. So obviously this relation is not symmetric. This relation is antisymmetric. Apart from this relation is also antisymmetric because here we are saying A is less than B. When we say 1 is less than 2, we cannot say that 2 is less than 1, right? So these two relations are antisymmetric. Apart from this, these two relations are transitive as well. You can check this on your own. So we can clearly say that R1 and R2 are reflexive, antisymmetric, and transitive. Now, it's the high time to understand the definition of partial order or partial ordering. A relation R on set S is called a partial ordering or partial order if it is reflexive, antisymmetric, and transitive. Simple definition, nothing fancy. A relation R on set S, this relation is defined on some arbitrary set S, and this relation is called a partial ordering or partial order if it is reflexive, antisymmetric, and transitive. The only difference between a partial order and an equivalence relation is that in case of equivalence relation we have symmetric property and not antisymmetric property. Rest of the properties are similar, right? Let's now understand what these properties mean to us. Reflexive means each element must be related to itself. We already know this. Antisymmetric means no two elements precede each other. This is important, right? This property is helping us in ordering the elements. No two elements precede each other means ordering, right? Forming the sequence. Transitive means first element related to second and second element related to third implies first and third are related. This is what transitive property is all about. Now, a set S together with relation R is called a partially ordered set or Poset. Very, very important. A set S together with relation R is called a partially ordered set, or we can also say that it is a Poset. Obviously, it is a short form of partially ordered set. Here P means partially, O means ordered, and this set means set. It is denoted by S, R, or sometimes we use this symbol to denote relation R. It seems like it is a less than or equal to sign, right? But it is not. This is not a less than or equal to operator. Actually, it is just a replacement of this relation R. We can also replace this symbol by R and say A, R, B means A is related to B. We can use these two interchangeably, okay? Here in place of R, we can use this symbol. They both mean the same, okay? Now, let's discuss one example. Show that the relation R, which is nothing but set of all ordered pairs A, B, such that A is a subset of B, defined on the power set of set S, which is equal to set of all elements like this, 1, 2, 3, is a partial order relation. We have to show this that this relation R, which is defined on the power set of set S, is a partial order relation. Relation R is said to be a partial ordering if and only if R is reflexive, antisymmetric, and transitive, right? We know that we have set S which consists of these elements 1, 2, and 3. Power set of set S consists of all these elements. Actually, these are the subsets of this set S. We know power set of S must consist of subsets of set S. First we have phi, then we have a set with element 1, set with element 2, set with element 3, then we have a set with these two elements 1 and 2, then we have set with these two elements 2 and 3, a set with two elements 1, 3, and a set with three elements 1, 2, and 3. These are all subsets of this set, right? This relation R is defined on this set, that is power set of set S. And we know that R is nothing but set of all ordered pairs of this form A, B such that A is a subset of B. Now let's see whether this relation is reflexive or not. Let's check the reflexivity property. We know that according to reflexivity, A must be the subset of A. Here obviously A belongs to power set of set S, right? And we know that this is true, obviously, because every element is a subset of itself. Apart from this, antisymmetric property says A is a subset of B and B is a subset of A implies A equal to B. Obviously this is true again. If A is a subset of B and B is a subset of A, then obviously A must be equal to B. We know according to transitivity, if A is a subset of B and B is a subset of C, then obviously A must be a subset of C. This is also true. So it is clear that this relation is a partial order relation. Isn't that so? Now let's see example 2. Show that the relation R, which is equal to set of all ordered pairs A, B such that A divides B, defined on the set S, which consists of 5 elements 1, 2, 3, 4 and 6, is a partial order relation. For this we know that relation R is said to be a partial ordering if and only if R is reflexive, antisymmetric and transitive. We know that we have this relation R, which consists of all ordered pairs A, B, such that A divides B, okay? Apart from this, we are available with this set which consists of total 5 elements 1, 2, 3, 4, 6. This relation is defined on this set. First, we will identify whether this relation is reflexive or not. According to reflexivity, A must divide A. Obviously, it is true, right? A divides A. There is no doubt about this. Apart from this relation is antisymmetric also. If A divides B and B divides A, then obviously A must be equal to B. This is only possible when A is equal to B. If A divides B and B divides A, then this implies A is equal to B. Let's see one example. We know that 1 divides 2, right? But 2 does not divide 1. But if we say that 1 divides 1 and 1 divides 1, then obviously they are equal, right? That is why it is possible. So if A divides B and B divides A, then this implies A is equal to B, right? Apart from this relation is transitive as well. If A divides B and B divides C, then A divides C. There's no doubt about this. So this relation is nothing but a partial order relation. But what do we mean by partial in partial ordering? What is the meaning of partial in partial ordering? We know what is the meaning of ordering, right? But what is the meaning of this partial in partial ordering? Why we are saying partial ordering? Are there any partialities? The word partial in partial ordering indicates that not every pair of element in a set is comparable. Okay, that is cool. But what is the meaning of comparable? Now let's just try to understand the difference between comparable and incomparable. This will help us in understanding what do we mean by comparable and incomparable. Here we are saying the word partial and partial ordering indicates that not every pair of element in a set is comparable. Not every pair, okay? That is why partial comes in partial ordering. Let's understand the difference between comparable and incomparable. The element A and B of poset S, R are called comparable if either A is related to B or B is related to A. Simple, right? The element A and B, we are talking about two elements of poset S, R. They are called comparable if either A is related to B or B is related to A. And the element A and B of poset S, R are called incomparable if neither A is related to B nor B is related to A. So here the word partial is quite justified because we are saying that not every pair of element in a set is comparable, right? Some relation is defined on a particular set. That relation is called partial order because not every pair of element in a set is comparable. Okay? This means we cannot say that every element is related to each other. Okay? That is why we are using this word partial in partial ordering. Now please remember, we can use S, R. We know that this symbol represents relation R to represent an arbitrary poset where A, R, B is used to denote A, B belongs to R. Now let's discuss one example related to comparable and incomparable elements. In the poset PS, the subset where S is equal to 1, 2, 3, 1, 3, this set is not subset of 2 or this set is not subset of this set. This set is not subset of this set, or we can say that this set is not subset of this set. Therefore, we can say this set which consists of two elements 1, 3 and this set which consists of just a single element 2 are incomparable, right? Obviously, we know that this is a poset. We have already proved this, right? Here you can see not every element is comparable, right? You can clearly see that this set is not a subset of this set and this set is also not a subset of this set. This means that this set which consists of two elements 1, 3 is not related to this set which consists of single element 2. Therefore, these two elements are incomparable, right? On the other hand, This set is a subset of this set, therefore we can say these two are comparable. Now I hope it is clear to you that what is the meaning of partial in partial ordering, right? Not every element is comparable in a partial ordering, okay? Okay friends, this is it for now. Thank you for watching this presentation.